In this video, I will show you another example of Clipper circuit. This will be example number 3. Find the output voltage and draw the output waveform for the following circuit using given input. This is our given Clipper circuit, and in this Clipper circuit we are applying a sinusoidal input whose positive maximum is plus 20 volt and negative maximum is minus 20 volt, and here we are taking the output from this terminal to this terminal. With this given sinusoidal input we have to calculate the output voltage and we have to draw the output waveform across this terminal to this terminal. Okay, now if you look at this Clipper circuit, you will see this Clipper circuit is the dual or combination Clipper circuit. Here the diode D1 and plus 5 volt source will form biased positive Clipper. And the diode D2 and this minus 10 volt source will form biased negative Clipper. As we have both biased positive and biased negative Clipper circuit, this will be combination Clipper circuit. And in this Clipper circuit we have two diodes, and we will consider the diodes as silicon diode. That means when the diode will be in forward bias, I will replace it with a 0.7 volt constant voltage source, and when the diode will be in reverse bias, I will replace it with open circuit. Now let me proceed with the circuit analysis. Look at this 5 volt source. Let's say this is our voltage source V1 and this minus 10 volt source is our voltage source V2. Now see, the positive terminal of V1 is connected with the N side and the negative terminal of the voltage source is connected with the P side of the diode D1. As positive terminal is connected with the N side and the negative terminal is connected with the P side of the diode D1, I can say that this 5 volt source is trying to drive the diode D1 in reverse bias. Now look at the 10 volt. This negative terminal is connected with the P side of the diode D2 and this positive terminal is connected with the N side of the diode D2. Okay, now see, as the negative terminal is connected with the P side and positive terminal is connected with the N side, I can say that the minus 10 volt source is trying to drive the diode D2 in reverse bias. Okay, now see, this is our input voltage from 0 to T by 2. This terminal will be at higher potential and this terminal will be at lower potential. Therefore, you will see during positive half cycle, this positive terminal is connected with the N side of the diode D2 and the negative terminal is connected with the P side of the diode D2. That means during the positive half cycle, due to the bias voltage V2 and the input voltage Vi, the diode D2 will always be in reverse bias. In that case, I can replace it with an open circuit during the positive half cycle. Now, this positive terminal is connected with the P side of the diode D1 and the negative terminal is connected with the N side of the diode D1. That means this input voltage Vi is trying to drive the diode D1 in forward bias, but this bias voltage is trying to drive the diode D1 in reverse bias. Therefore, during this positive half cycle, we will have two cases when Vi will be greater than 5 volt. In that case, you will see when Vi will be greater than 5 volt. Let me indicate 5 volt here. This is our maximum voltage 20 volt. If I indicate 5 volt, you will see, let's say this is our 5 volt. Okay, When Vi will be greater than 5 volt, the effect in this direction will be greater than the effect in this direction. Therefore, the diode D1 will be in forward bias. By the input voltage Vi, because it will minimize the effect of the bias voltage. In that case, I will replace the diode D1 with a 0.7 volt source because this is a silicon diode. Another case is possible when Vi is less than 5 volt. That means from this point to this point, Vi is less than 5 volt. When Vi will be less than 5 volt, the effect of this bias voltage will be greater than the input voltage Vi. As a result, you will see this bias voltage V1 will put the diode D1 in reverse bias. In that case, I will replace the diode D1 with an open circuit. Okay, now let me draw the output waveform. During positive half cycle, the diode D2 will be in reverse bias, so we can replace it with an open circuit. That means I can remove this D2 from the network. That means I can remove the entire branch that contains the diode D2 in this circuit. And here we have two cases. When Vi is greater than 5 volt, this diode D1 will be in forward bias. In that case, I will replace the diode D1 with a 0.7 volt source. Let me do that. After replacing the diode D1 with a 0.7 volt source, I will get a circuit like this. Now see, we are taking the output voltage across this terminal to this terminal. That means we are taking the output voltage from this terminal to this terminal. You will see between these 2 points we have two voltage sources, 0.7 volt and this 5 volt. As they are sharing same polarities, therefore I can say our output voltage will be equal to 5 volt plus 0.7 volt or 5.7 volt. That means from this point to this point, as long as Vi will be greater than 5 volt, our output voltage will be fixed at 5.7 volt. Now consider this case when Vi will be less than 5 volt. When Vi will be less than 5 volt, the diode D1 will be in reverse bias by this voltage source V1. As a result, I can replace it with an open circuit. If I replace the diode D1 with an open circuit, I will get a circuit like this. Now see, in this circuit, the current flow I will be equal to 0 because there is no path for current flow. Therefore, the voltage drop across this 10 kilo ohm resistor IR will be equal to 0. So you will see our output voltage VO will be equal to VI. That means our VO follows VI when VI is less than 5. That means our VO will have the same waveform as our VI as long VI is less than 5 volt. See, from this point to this point, Vi is less than 5 and it is changing like this. So our output voltage will have the same waveform. From this point to this point, our Vi is less than 5 volt. So it is changing like this. Output voltage follows input voltage. So it will have the same waveform. Okay. So this will be our output waveform during positive half cycle. Now consider the negative half cycle or the voltage between T/2 to T interval. During negative half cycle, this terminal will be at lower potential and this terminal will be at higher potential, and the negative terminal of the input voltage Vi is connected with the P side of the diode D1 and positive terminal is connected with the N side of the diode D1. That means both this 5 volt source and this input voltage Vi are driving the diode D1 in reverse bias during this negative half cycle because their positive terminal is connected with the N side and negative terminal is connected with the P side of the diode D1. So during negative half cycle, the diode D1 is in reverse bias due to the bias voltage V1 and the input voltage Vi. So we can replace that with an open circuit during negative half cycle. Now see, the negative terminal of the input voltage is connected with the N side of the diode D2 and positive terminal is connected with the P side of the diode D2. As the positive terminal of the input voltage is connected with the P side and the negative terminal is connected with the N side of the diode D2, that means Vi is trying to drive the diode D2 in forward bias, while this 10 volt source is trying to drive the diode D2 in reverse bias. Therefore, we will have two cases when our Vi will be greater than minus 10 volt. Another case is when Vi will be less than minus 10 volt. Here Vi is greater than minus 10 volt. What does that mean? See, this is our minus 20. So minus 10 will be halfway between 0 to minus 20. So let's say this is our minus 10 volt. Vi is greater than minus 10. That means I am talking about this region. Vi is less than minus 10. That means I am talking about this region. Okay. And this is our separation point of minus 10. See, when Vi will be greater than minus 10 volt. See, when Vi will be greater than minus 10 volt or when Vi will be in this region, you will see the diode D2 will be in reverse bias due to this V2. In that case, I can replace that with an open circuit when Vi will be less than minus 10 volt. That means if I talk about this region from minus 10 to minus 20 region, you will see the effect of the input voltage will be greater than the effect of this V2 voltage source. Therefore, the diode D2 will be in forward bias due to the input voltage Vi. In that case, I can replace that with a 0.7 volt voltage source. Now let me draw the output waveform. During the positive half cycle, D1 is in reverse bias, so I can replace that with an open circuit. That means I can remove this entire branch from the network. Now when Vi is greater than minus 10 volt, in that case the diode D2 is in reverse bias, so I can replace that with an open circuit. If I replace the diode D2 with an open circuit, you will see the current flow through this path will be equal to 0 because there is no closed path for current flow. As the current flow I will be equal to 0, therefore the voltage across this IR will be equal to 0. Therefore you will see our output voltage will follow input voltage. VO will be equal to VI. Output is following the input voltage. What does that mean? From this point to this point, our input voltage is changing like this. So our output voltage will follow the input waveform of Vi. From this point to this point, our input is changing like this. So our output voltage will follow the input voltage Vi. Okay. Now consider the last case when Vi is less than minus 10. That means I am talking about this region. When Vi is less than minus 10 volt, our diode D2 will be in forward bias due to the input voltage Vi. In that case, I can replace the diode D2 with a 0.7 volt source, and the convention of replacing a diode is like this. If I have a diode like this and it is in forward bias, I will connect the positive terminal of the voltage source at the P side of the diode D and the negative terminal at the N side of the diode D, and I will replace that with a 0.7 volt source. After replacing the diode D2 with a 0.7 volt source, I will get a circuit like this. Now see, we are taking the output across this terminal and this terminal, and between these two terminals I have two voltage sources, 0.7 volt and this 10 volt. Their negative terminal is in upward direction and positive terminal is in downward direction. That means they are sharing same polarities, but we are taking the output across this terminal to this terminal. So our output voltage will be equal to minus 10 minus 0.7, which will be equal to minus 10.7 volt. So from this point to in this region, our output voltage will be fixed at 10.7 volt. Okay, minus 10.7 volt, and this will be our complete output waveform. From this point to this point, our output voltage will follow the input waveform, and when Vi will be greater than 5 volt, our output voltage will be fixed at 5.7. From this point to this point, our output voltage will follow input waveform. Okay, from this point to this point, our output voltage will also follow the input waveform. When Vi will be less than 10 volt, our output voltage will be fixed at minus 10.7, and from this point to this point, output voltage will be following the input waveform. Now let me show you the circuit simulation. See, this is the circuit I set in the simulator, and this is the output response of that clipper circuit. If you look at the circuit, you will see from this point to this point, our output is following the input voltage. After that, it is being fixed at a voltage of 5.73 volt, and it will be 5.73 volt up to this point. After that, our output voltage will follow the input voltage up to this point, and at this point our output is being fixed at minus 10.7 volt. After that, from this point to this point, our output voltage will follow the input voltage. Okay, that's it. Thank you.